A sequence is simply a list. You will see three different types of sequences on this page. You can see first off, we have an infinite sequence, and I can tell it's infinite because of the ... I have 4 numbers listed, separated by commas, so that's how we'll write our sequences. And that I can see a distinct pattern, but it doesn't have to show a distinct pattern. The next sequence I have is a finite sequence because there's no ... And this one again has a pattern, even though it's kind of weird, 4, 4, 4, 4. This last sequence here is another finite sequence. Again, no ... but I don't see a pattern here, and that's okay. We're mostly going to work with sequences that have patterns, but it's okay if they don't have one. The terms of a sequence are the numbers listed in it. So when we look at the sequence 5, 10, 15, we can say it has 3 terms. 2, 4, 6 has infinite terms. There's some standard notation that we'll be using as we learn about sequences. When you see the letter A, we're referring to term, and then its subscript is the term number. So for that sequence where we had 5, 10, 15, I can say that A1 or term 1 is 5, and A2 or term 2 is 10. I can also generalize this and find an expression for an, or the nth term in the sequence. And that's where we're going to start looking for patterns. So in this case, I can see that this is just multiplying the term number by 5. So term 1 times 5 makes 5. Term 2, when I take 2 times 5, that's 10. So I can just write this expression as 5n, where n represents the term number, and we're taking that term number times 5 to get the term itself. We're also going to be working backwards a little bit through our sequences and given a sequence, writing an expression to represent that for any value of n. So I can see here I have 2 different sequences. One of them is just 0, 1, 2, ... The second one is 7, 13, 19. What helps me to think about is what is the term number for each of those expressions? And then how does that term number relate to the term itself? So for that first sequence, I've highlighted my term numbers, A1, A2, A3. And I can see that each of the terms themselves are 1 less than the term number. Remember, the term number is n. So if I just take 1 away from each of those term numbers, I can see what the term is itself. And then check it. If n equals 1 for your first term, you would say 1 minus 1 is 0. If n equals 2, as we move on to the second term, 2 minus 1 is 1, etc. And then I could find any term in the sequence. The second one's not as obvious. But again, I've labeled my terms, A1, A2, A3, and my goal is to find the relationship between the term number and the term itself. I can see that if I were to think about this first term, if I multiply it by 7, that works. But then when I move on to when I move on to the second term, it doesn't work as well, and neither does it work the third time. What if we add? If I add 6 to my first term number, I get the first term. But again, that doesn't work for any of the others. So what I'm thinking is it's combination. I can see in this sequence that these numbers are increasing by 6 each time. So maybe it has something to do with 6s. So think about taking your term number times 6. If I took 1 times 6, I would get 6, but then I would have to add 1. Okay, and that's 7. Does it work again? If I do 2 times 6, that's 12, and then I add 1. Okay, it worked for the second time. And 3 times 6 plus 1 makes 19. And if it works for all 3 of those terms, I can be pretty much assured that it's going to work for the whole sequence. So this is just going to be some trying and playing with numbers and seeing what works. Just make sure you check each of your terms after you've written your sequence to make sure it holds true. When we're working with a recursive sequence, we can't just jump to a specific term in the sequence without knowing the terms before it. So if I give you a recursive sequence, we know it's recursive because of the k that's built in as opposed to the normal n. And I ask you to find A4 or term 4. You're not going to be able to find term 4 without knowing term 3. And you're not going to find term 3 without knowing term 2. And you can't find term 2 if you don't know term 1. So that's the recursiveness of the sequence. It really builds on itself. Okay, so I have the sequence 2 times a, k minus 1. That k minus 1 just means the term before k, plus 7. And I know that a1, or the first term in the sequence, is 3. So I can use that first term now to help me find the second term. So again, 2 times the term before. So 2 times 3 plus 7 must be my second term. And that is 6 plus 7, so 13. And now I can use that term to find the third term. So the third term is 2 times the previous term, 2 times 13 plus 7. So that's 26 plus 7, which is 33. So term 3 is 33. And then I can jump to term 4 and say, okay, 2 times the previous term, so 2 times the 33 plus 7. That would be 66 plus 7 is 73. So again, there you see how the recursive sequence really builds on itself. I couldn't ask you to find the 10th term, or I could, but it's going to take a lot of work because you'd have to know the first 9 to get there. See a new operation pop up every once in a while, which is kind of fun. It's called the factorial. And the factorial looks like an exclamation point, and it is just an exclamation point. And what it means is when you see a factorial after a number, like n factorial or 7 factorial, we're going to turn this into a multiplication. It's taking that original number times all the numbers that come before it until you get all the way down to 1. So n factorial we can say is n times n minus 1, n minus 2, n minus 3, etc. Or more specifically, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we would multiply all those together and get some number. So let's think about this fraction of 8 factorial over 5 factorial. So I'm going to write out some terms. 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we could go ahead and multiply all those out together. But then I also want to consider the denominator. 5 factorial, 5 times 4 times 3 times 2 times 1. And do you see that we have some common terms that we can actually cancel out? The 5, 4, 3, 2, 1 in the numerator can cancel out with the 5, 4, 3, 2, 1 in the denominator, and we're left with 8 times 7 times 6, whatever that value is. Now, on your calculator, you do have a factorial button. So I want to show you where that is. So let's say, for instance, we were doing 7 factorial. So I'm going to type in my number, 7, go to math, and then scoot over to where it says prob. Factorials are used a lot with combinations and permutations. So math and then prob. See number 4 is that factorial or that exclamation point. And when we hit enter, we get the product of the numbers from 7 all the way down to 1. Now, a couple fun things. Obviously, 1 factorial is just going to be 1 times 1, right? So that should just be 1. But look what happens when I do 0 factorial. 0, going over to prob. 0 factorial is also 1. That should surprise you a little bit. And it's, again, defined using the combinations and permutations. Think about negative numbers. What would happen if I took a negative number and did a factorial with it? That is an error, and that should make sense because we can't take a negative number and work down to get the number 1. Okay, I'm going to quit that. What about a fraction? So what if I took a half? That's interesting. And actually that number should maybe not look somewhat familiar, but that actually is defined using pi. I'm going to find an example of it if I can, and I'll put it in here. But just kind of when you get some decimals and fractions, you get some neat relationships. But anyway, factorial button, math, go over to prob, and then option number 4 is your factorial. As we work our way through sequences, we're not going to stop at just finding specific terms of a sequence or writing their expressions. We're also going to be adding them together, finding the sums of sequences. A shortcut way of writing a sum is the Greek letter sigma. And it takes some practice in writing, so practice writing them. So this uppercase Greek letter sigma literally means sum. We are adding. Now, parts of our sigma notation here are the bottom and the top values. So you'll see your variable at the bottom, and then we have what we call the lower bound. This is the first value of the variable that we will be plugging into our expression. The top number, what's on above our sigma, is the last number we'll be plugging in. So this tells me with my an, or my expression of 5n plus 3, I'm going to start by plugging in the number 3 to my expression. So let's go ahead and do that. So when I plug in the number 3, I would have 5 times 3 plus 3, and that is the first term in my sum. And then I'm going to add to that the next term in my sum. So if I've started with the number 3, I'm going to work my way up to 7. So next would come 4. So now if I plug in 4 for n, I would have 5 times 4 plus 3. And now I'm going to go to 5. So if I plug in 5, I would have 5 times 5 plus 3. And then 6. 5 times 6 plus 3. Ooh, that was ugly. We got to switch that up a little bit. And then lastly, and I know it's last because it's that top number. So lastly, I'll plug in the number 7. So 5 times 7 plus 3. So that's what this expression represents for us. I've given the expression an, and I know the first number to plug in for n, and then the last number to plug in for n. And then we'd actually have to go back and find these values and add them up. So it's that 15 plus 3, 18, plus 20 plus 3 is 23, and then 28, and then 33, and then 38, and then add those together to get one final sum. So that is your sigma notation.